The mission of IEEE students is to deliver a common, high-quality IEEE student membership experience globally for lifelong professional membership through IEEE.
IEEE is a family. The friends you build through volunteering stay there. You really make friends for life.
Getting involved at your local student branch, your local section, and your larger region is one of the many benefits that IEEE students have. You can also apply for a variety of awards, both as an individual and as an IEEE student member of your local branch. You can also get involved in a variety of contests and competitions, including our #1 student competition, IEEE Extreme, a 24-hour global coding competition with over 8,000 students involved annually. IEEE Potentials is a premier student magazine. It provides you with the opportunity to get published and to review your peers' work as well. With over 400,000 members in the IEEE Global Network, you can get connected, find a mentor, and also collaborate with professionals in your field.
If you want to do something to impact your community through IEEE, it gives you the resources.
You can make the most of your IEEE membership by completing your profile. It allows us to contact you and keep you up to date with what's happening at the global IEEE offices. Take advantage of being an IEEE student member by collaborating on projects within your local student branch and your section with professional members. By collaborating on projects, you have the opportunity to get featured on IEEE TV. We'll see you there.
EPICS in IEEE empower students and local communities around the world to apply engineering to solve those challenges.
The IEEE Event Finder allows you to locate conferences, meetings, events, and activities in your area and worldwide. You can get involved in a variety of special interest groups as well. Women in Engineering, Standards, and IEEE Young Professionals.
YP represent!
Of course, that's when you graduate. Remember, IEEE prides itself on being your professional home. Be sure to take advantage of everything the IEEE has to offer.
The more you put in, the more you get out.
We share the same fears, we share the same hopes, we share the same visions, and this is the best place we can exchange our experience, and at the same time we can get support from our experienced colleagues at the same time. It's perfect.
My name is Hao Yao Chen, an IEEE member from Harbin Institute of Technology, Shenzhen. I am also a member of IEEE Robotics and Automation Society. When I was a child, I was quite interested in making toys by myself. When got admitted to University of Science and Technology, I chose engineering without hesitation. I was quite interested in environmental sustainability, especially that in the countryside. By collaborating with Professor Liu Yinghui from CUHK and Professor Zhang Shiwu from USTC, we are trying to develop a framework that combines mobile ground robots, amphibious robots, and unmanned aerial manipulators together. In that way, multi-robots operated in different areas can be networked to cooperate with each other. We are exploring to use multi-sensors to realize robust and long-term navigation in complex GPS-denied environments. The fusion of different sensors can provide useful information about robotic localization and environmental map building. On the basis of these algorithms, robots can automatically implement the assigned tasks. We are trying to develop autonomous robots for assisting or replacing people to implement dangerous tasks. Our research can benefit many other industries such as search and rescuing, industry transportation, agriculture, logistics, and so on. Although there exist many challenges, I am optimistic about the robotic solutions for environmental sustainability. In the next 5 to 10 years, more and more robots will be applied in environmental monitoring, pollution control, and so on. Environmental sustainability is an interdisciplinary field. We are looking forward to cooperating with researchers from robotics and other fields to overcome the challenges in this important area.
Greetings everyone, and welcome to the continuation of the virtual talks of the B branch of the IEEE. My name is Denis Flores, and I am going to be part of this, also moderator of this presentation. I am part of the B branch, where B stands for Bordeaux Electrical Engineer. And this is the third day of our talks, here having the pleasure to receive Dr. Gabriele Manganaro, today from Analog Devices. But before proceeding to the talk, I would like to present you some next events that we are going to take in place for the B branch and another interesting subjects that you might be interested. Our next talk is going to be given by Professor Gerald Yu, and it's going to be more focused in body area network, connecting things together around the body. There are going to be several talks during the month of November, given by myself, Orgon Alek, from University of Poland. Is more focused in microelectronics, going in 3D. And Thursday 12th, from Andrei Vladimirescu, from the University of Berkeley and the ISEP in France, more focused in simulations, measurements, and in electronics. On Thursday 26th, Jean-Michel Redondet, from the University of Liège of Belgium, with the subject of a structural approach for MAI-resistant IC design. And finally, the Thursday 27 by Victor Greenwald from Synopsys Chile. It's more focused in the soil mixture and soil temperature impact on ground and crop growth. There are going to be also several events in Brazil and Argentina, which are going to be held by the IEEE, the IEEE CAS, and the given more focused in the industrial talks. During this year, it's going to be performed by Facundo Pico, who is a system architecture of the University of Porto Alegre do Brasil. There is going also to be the last CAS event the next year in Peru, in the month of February, from the 21 up to the 24, which are going to be held by the IEEE. There is going to be also given the third edition of the IEEE CAS in Rio Grande do Sul. This is going to be performed several workshops where going to be held. And there are going to be several interesting topics given by several professors of around the world focused in the microelectronics. There is some interesting event focused in the aerospace field, which is called ACT in Space 2020, which is going to be held in the days of 3rd and 14th of November, and is going to be done virtually, and it's going to be an edition from Bordeaux also. And finally, the night of the Researchers European, which is going to be held around several places of Europe, and it's going to be also a meeting here in Bordeaux. Finally, this is the seasonal school of the IEEE held here in Bordeaux, which is more focused in the circuits and system for IoT, and it's going to be the first edition in the next year of May. Okay, and now I would like Professor François Rivet from the University of Bordeaux to give the welcome to our guest.
Thank you, Denis. So I would like to thank Gabriele for his talk today. It's very important to show our students that IEEE is not limited to professor or academics, but the industry is a huge part of IEEE. And Gabriele has an exquisite experience through different companies about designing circuits. And the last one is analog device. And I'm sure that students will appreciate your talk. Just to mention that Gabriele is talking right now live from Boston in the USA, and just to see that how the world of IEEE is small and we stay all connected together. Thank you.
Thank you, Professor. Before the talk, I would like to give a quick biography of Dr. Gabriele Manganaro. So, Gabriele Manganaro holds a doctoral in engineering and a PhD degree in electronics from the University of Catania in Italy. Starting in 1994, he did research with IST Microelectronics and Texas A&M University. He worked in data converters in integrated circuits design at Texas Instruments, Engine Incorporated, and as design director of National Semiconductor. Since 2010, he has been working with analog devices, first as an engineering director from high-speed data converters, and more recently as a technology director for the communication product division. So in fact, he is a professional more focused in the industry. So this is going to be very interesting. Now I will let Dr. Gabriele Manganaro to take the lead of the presentation. So enjoy the presentation.
Thank you very much. Good morning, good afternoon, good evening, and thanks for inviting me. I have a presentation that touches on several different aspects of ultra-wideband systems design. And I'm actually going to begin by sort of giving you the final conclusion of the presentation, which is essentially that in the design of wideband signal processing systems, which we will soon better understand what it means, there are many different technologies that come into play. And it's in fact a multidisciplinary type of design, and there are different trade-offs that are involved between the technologies that are involved. And so it's very important that we even when we concentrate on one particular technology, which may be mixed signal IC design, or it may be algorithmic design, and so on, we understand that the trade-offs between the different aspects are important, and therefore we need to have a also good understanding of the whole. So let's start with getting a better understanding of what do we mean for wideband signal processing systems. And so the best way to start is to look at what applications are driving the development of such systems. And in recent years, there has been an emergence of new applications in both the automotive space, as well as in the communication technology space, et cetera, et cetera. And as a result of these multiple trends, there are many commonalities. One of the aspects that is common to all these emerging applications, it's actually communication. Robots that need to be controlled, cars that are becoming more autonomous, and they of course need to be able to sense the environment and respond and connect to the internet. And of course, we have communication systems that are ranging from smartphones, tablets, Internet of Things in general. Now, all these different applications again require communication systems, that enable the functionality and enable connecting to internet, where also we can have remote processing. Now, one thing is that is emerging is that many of these applications are demanding for higher and higher data throughput. And data throughut, of course, is a result of a combination of dynamic range and bandwidth, or rather the ability to transfer data depends obviously on the combination of dynamic range and bandwidth. And provided that the dynamic range, for a number of reasons in many applications, it's of the order of, let's say, 10 to 14 bits. The other variable, of course, is bandwidth. And so to get higher and higher throughput, many applications, we're looking for wider and wider bandwidth. And I'm listing in this slide some of the emerging applications that are really becoming very important for today or for the future, such as wireless communication. We talk about 5G, but people are already talking about 6G. And obviously, data centers, which require a large amount of data to be transferred, and other applications such as virtual reality, remote medicine. Obviously, with the present situation with the pandemic, these are all communication links are definitely becoming very important for us, and obviously broadband sensing and et cetera, et cetera. Now, many of these are emerging communications that are developing. And some of them, they're really in the early stages of development. And so it's going to be difficult to tell, let's say, 4 or 5 years from now, which of these will emerge as the driving applications that will drive business and they will, obviously drive technology development. But one thing that all these have in common is the requirement for higher and higher bandwidth. So if we focus on wireless communication as one of the drivers, we can see that the spectrum available, especially the so-called ISM spectrum, or in general the spectrum below 6 gigahertz, is extremely crowded. There is everything. There's radio, TV, cellular system, Wi-Fi, etc. And if we go to higher frequency, there are opportunities to find larger ranges of frequency where we can actually allocate wider bandwidth. And this plot here shows you the attenuation at the different frequency ranges. And obviously, as you can see, there are peaks where there is large attenuation, and obviously that's very difficult to sustain a link in those frequencies. But in between, there are very wide ranges of frequency where there is plenty of bandwidth available. Now, obviously, the challenge is that at the higher and higher frequency, there are many technology challenges, and also there are effects that come into play and introduce attenuation. But let's get into that in a minute. Now, when we design systems that are required to process signals in such a wide bandwidth at such a high frequency, there are multiple constraints that need to be met. And you can look at this as almost like an exercise in finding the bottlenecks and relieving the bottlenecks. And the bottlenecks are really all the constraints for bandwidth, for noise and linearity, and it come into play in different technologies. So for higher bandwidth at a higher center frequency that comes from the application, we have technology constraints, such as the ability of mixed signal systems to operate at that frequency and to sustain dynamic performance over a wideband. And then, of course, there are business constraints, such as what will it be the cost of developing a system like this, and will we get a return, a commercial return, if we are able to build a system like this. So there is a constant series of trade-offs between, again, the demands of the applications, which define the specifications for our design, the actual technology constraints, and how we can overcome these limitations, and obviously business aspects such as is a technology cost effective? Is there a better way? Will we get enough return? So if we look at the entire stack of abstraction, going from devices and process technology to circuits, architectures and functions, and up to system, and ultimately up to the application and software layer, there are constant trade-offs that are being made between one level of abstraction or the other. Such as, for example, if I adopt a faster process, I will be able to design circuits that can handle wider bandwidth at higher frequency. But of course, that will come at a cost. So can I actually then change the architecture and be able to meet my specifications with a different set of circuits and so on? And that's just an example. Now, in addition to the classic circuit design and electrical engineering design that we are probably more familiar with, algorithms are also coming to the rescue, are coming into play, and are helping in the form of calibration, in the form of linearization for systems, etc., etc. So that's another set of technologies that come in support to the one that I sketched over here. Now, another aspect that needs to be considered is also the aspect of packaging technology. Where obviously appropriate packages needs to be considered when there are challenges in extracting the heat that is the result of high power consumption, the manufacturability, and will this product meet the specifications over the prescribed lifetime, and so on and so forth. Will we be able to fit all of that in a prescribed space, and so on? So at the end of the day, even though we concentrate in particular aspects of the design, which may be circuit design or maybe architecture design, etc., we need to understand there is a constant trade-off between the different abstraction levels. And it's and because of that reason, it's actually not very realistic to think that a design that is top-down only, or a design that is bottom-up only, will actually be the way out of these trade-offs. In fact, even though structurally it's appropriate to do a top-down design, in most cases, we have to go back and make trade-offs at different levels of abstraction. And while we do these trade-offs in terms of engineering design, we also need to keep in mind some cost trade-offs, because obviously every engineering choice, every design choice has an implication in terms of the costs of designing, the cost of the selection of the technologies. So let's focus on the example of wireless infrastructure. Wireless infrastructure is a fancy word to say essentially base station. Base station is obviously where all the smartphones or the other wireless user devices connect in order to gain access to the internet. Now, in wireless mobile wireless communication, we have seen, of course, a number of different technologies and generations, and presently looking at wireless communication for cell phones, etc., etc., we are at the beginning of what people are referring to as 5G, fifth generation. And for that, there are different bands that are shown in this diagram over here, allocated at different frequencies. And generally speaking, people are talking about sub 6G, or basically when the bands are located below 6 gigahertz, and then millimeter wave. And this is the range for sub 6G bands. And example of millimeter wave are those for bands that are going to be allocated at a center frequency of the order of 24 to 30 gigahertz, which is becoming a very popular choice. And then also in the 37 to 50 gigahertz. And in future, there is already discussion about bands at around 60-something gigahertz and beyond for emerging applications, even in the 100 to 140 gigahertz. So those are those that we term as millimeter wave bands. Now, 5G is in fact not simply cell phones, but in fact it's meant to address a large variety of different applications, which include even those associated with autonomous vehicles, self-driving cars, and augmented reality, etc., etc. So it's not just about the bandwidth or the data throughput, which again can be fairly intensive, especially for applications such as video streaming, but also for certain sensing applications and for virtual reality. But it's also some of the innovations imply a reduction in latency in order to address applications where you need to have a very prompt reaction between the remote unit and the control. And this, as you can imagine, include things like autonomous driving, but also telemedicine, etc. Now, another thing that that 5G is trying to address is not just the amount of data throughput between the base station and the client devices, but also the ability to connect with more devices at the same time. And so, as you can see in this plot, in 4G, even though base stations, this is a base station and these are the client devices, can connect to multiple devices over a certain distance using an antenna, which is in fact more and more becoming a phased array. One of the innovations that people are working on in 5G is actually to use a true set of different beamformers in order to use the same antenna array to simultaneously create independent links between the base station and the user devices. Now, to do that, then antennas and base stations are actually changing quite rapidly. And so we're going from the older generations of base stations, which were consisting in a single or set of antennas doing a more broadcast and the base station containing all the electronics sitting separately from the antenna, into newer and newer generations. So you can see here on this side where it's not an antenna, it's actually a large antenna array. In fact, many of the antennas are controlled independently. The radio unit, in fact, moves together with the antenna, and then it is connected to the actual digital baseband unit, which is separate. And by doing so, we can actually begin doing beamforming And therefore, we can start creating independent directional beams between the base station and the different user units. And so here are some photos of such antenna arrays. This one is in the case of sub 6G, so in other words, less than 6 gigahertz. And one thing that I want to bring your attention to is that in order to be able to create a beam and avoiding artifacts, which people typically refer to as grating lobes. So in other words, some areas where the energy it's actually formed, that it's not in the location that is intended. One requirement is that the distance between the different antennas in the array needs to be at most λ/2, where lambda is the wavelength of the frequency that you are transmitting or receiving. Now, for 5 gigahertz, for example, λ/2 is of the order of 3 centimeters, which means that in this array of antennas that you see here, the distance between one antenna and the next one, it needs to be 3 centimeters or less. Now, if you think that we need to also be able to control each antenna, ideally with electronics, so you can see the electronics will have to sit behind these antenna arrays. And if the distance is 3 centimeters, there isn't a whole lot of space to place all the electronics. So that's a challenge. And it's also a manufacturing challenge. Another challenge has to do with heat dissipation. Now, when the power consumption associated with the electronics, and we'll look into that in a minute, generate obviously heat, and this heat is concentrated into a relatively small physical area, then that's a problem, because now obviously you're dealing with manufacturing issues, you're dealing with reliability issues, and that needs to be taken into account. So I think you're starting to see how there is now an immediate trade-off that needs to be accounted for.
It's time for lunch.
Between the heat that you are able to dissipate, between the power that you are able to deal with, and the ability for your circuits to operate. So let's look at diagram representing the signal chain in an antenna array like the one we have seen. So you have over here the array of antennas, and each antenna is used to both transmit and receive. So there is a filter that we'll look into in a minute called a duplexer, and then you have the power amplifier for transmit and the LNA for receive. And this set of antenna arrays is actually partitioned into subarrays. Each subarray has a corresponding analog beamformer, which essentially combines the transmit and receive paths for the subarray. And then you have with these subarrays, you actually form a digital array. And then each subarray goes to a modulator-demodulator stage, which performs the baseband to millimeter wave or high RF conversion, or down to an intermediate frequency. Then you got the data converters, the D2A and the A to D. And then once you're in the digital domain, you can perform filtering, down digital up conversion and down conversion. And eventually all these data streams, each one associated with an analog subarray, Then it goes to the actual digital beamformer, which obviously controls and combines all the signals. And for each digital beamformer, you can control and realize an independent beam, and so you can connect with each with a different device. Now, at every one of these interfaces between the functional blocks, you're going to experience bottlenecks. Will we have enough bandwidth? Will we have enough dynamic performance, so noise and linearity? Will the data rate be compatible with our power constraints? Can we move this data in and out of different chips or different packages? So all of these are challenges, and all of these imply trade-offs. So let's look at one of these many signal chains for a complete receive and transmit path. So you have the transmit path up here and the receive path up down here. The front end part, the one that operates at between intermediate frequency and RF or millimeter wave, is composed by the antenna, of course, by the duplexer, which is a filter that allows to use the antenna both in transmit and receive and minimize the amount of power that couples from the transmit into the receive. And then filters in order to eliminate undesired content, the images, etc. And then we have the mixers, which are all driven by an oscillator, which of course sets the center frequency. And then finally, you go to typically baseband, where you have the converters, which are clocked by another oscillator, and then the baseband processing, which as I explained, include, of course, filtering, additional filtering, possibly down conversion, up conversion, and then eventually the beamformer. So this part is the millimeter wave front end, and this other part is what we call generally the RF transceiver. Now, the millimeter wave front end is typically done either in a 4 millimeter wave is done typically using by CMOS technologies, while generally speaking, much of the RF transceiver is done in CMOS. Now, of all these blocks, there are different trade-offs and challenges. But for example, we can immediately point out that in terms of power consumption, a lot of the power consumption happens at the PA. The PA needs to deliver the power to be transmitted to the antenna. PAs tend to be power inefficient. The efficiency of a PA typically is between 10 to 20%, which means that the remaining 90 to 80% of the power actually becomes heat, and so it needs to be removed in order for it to continue working well. And so think back at this antenna arrays, all this heat needs to be dissipated. The other blocks, of course, in this chain also consume quite a bit of power, and so there needs to be proper budgeting at the interface with the converters, and especially the baseband processing in the digital front end that sits behind it. They can be very power hungry, and so for that reason, these blocks generally are done in CMOS, and in fact, especially the baseband processing is done in very fine lithography CMOS. Now, there is another problem. The other problem is that while most of these functional blocks can be integrated, think of, for example, about this part on the left, which goes integrated and the benefits of Moore's law. This part, not much, but the real problem is that there are also many discrete components, and the discrete components that actually do not scale and do not benefit of Moore's law, including the cost implication of Moore's law, are the filters. And the duplexer is an obvious one. So yeah, the problem is that many of the filters, especially those used for the RF part, are discrete. They are expensive, and their performance also depends on the size. And think of it again in terms of size, because we go back to a relation between the frequency and the wavelength. And so many of these blocks, which typically use cavities and other rather bulky elements, don't scale. Don't scale with Moore's law, and they are expensive. So this one is to get you a sense of what we're talking about. What we're looking at here is it's actually a rather old duplexer. It's for a third generation base station. So obviously there has been much progress in this sense. But to give you a sense, you can see yours truly here holding one such duplexer. So obviously this is rather large, expensive, and it requires tuning. That's what all these little screws are. And what about the power? I alluded to the power in the power amplifier. So this is a power amplifier. Again, it's an old power amplifier of an old base station, but it gives you a sense that we're really talking about large objects here. So this is not the electronics and benefits of Moore's law and scales into very small size. And as you can see here on the back of the power amplifier, this is the heat sink. This is the back where this sits. So that's quite a bit of heat that needs to be removed. So with that in mind, let's begin looking at the technologies that can help us solve this problem, starting from device technology. So first of all, Moore's law. In recent generations of CMOS and FinFET, we have seen a continued level of integration. So Moore's law, in terms of how many transistors can you cram in a given area, it's actually fairly alive. And in a sense that indeed the size reduction continues, and it's expected to continue into new nodes such as 7, 5 nanometers, and who knows, maybe 3 nanometers and beyond. In terms of performance of the devices, for digital performance, the gate delay of digital blocks continues reducing. So devices, digital function tend to get a little faster, though definitely not at the same rate of improvement that we would have seen even 10 years ago. So there is some improvement in terms of speed. The main improvement in terms of digital functions is really in the switching energy. So essentially the energy that is spent to perform a given digital function. So that part is well. In terms of speed, again, not much more, but definitely in terms of miniaturization, in terms of area, we continue seeing great benefits. So what do we do with that? Well, here I plot some figures of merit, which I guess can make us draw some conclusions. So we're again looking at the example of wireless infrastructure, so base stations. Now, the demand from generation to generation for bandwidth, what we call instantaneous bandwidth, has been increasing. At this time, it was common to deal with bandwidths of the order of 75 megahertz, which quickly around this time became 100 megahertz, 200 megahertz, 400 megahertz, and more recently, systems like this demand for 800 megahertz to 1.6 gigahertz. So this is the blue curve. The demand for instantaneous bandwidth has been increasing quite rapidly. You should keep in mind that these normalized scales here are logarithmic. And so over a linear increase of time, you have a very accelerated pace in terms of what type of bandwidth do this system need to be able to support, to process. Can this be supported by devices? Well, unfortunately, the answer was okay a few years ago, about 10 years ago, not anymore. This is shown by the plot of FT, the transition frequency of devices for nodes, which are implied here, which are 65 nanometers, 28 nanometers, 16 nanometers, and then in the future 7 or 5 nanometers. So the FT of the devices have improved, for example, from 65 to 28, and kind of changed, but not a lot more in 16, and although it's improving with newer generations, and improves a little bit, but not a whole lot. What has improved, as I mentioned before, is the power of the digital functions. Another thing that has, and that's the purple curve. Another thing that has improved, if you look at another figure of merit for the quality of a process technology, is the transition frequency FT times the transconductance efficiency, the GM over IT. So if you look at this figure of merit, that has been constantly improving. This figure of merit is essentially trying to measure the combination of the ability of the process to go fast, that's FT, while being power efficient, which is the transconductance efficiency. So what is the message over here? Well, the message here is that during this time, if you had a mixed signal system, such as a data converter or any other, you could have ported it from one process generation to the next without major architectural changes. Of course, at circuit design level, you would have needed to make some improvements and block level improvements. And but by and large, you did not need to dramatically change the architecture. However, as the demand for bandwidth has outpaced the ability of the process technology to support it, then we have been forced to make an architecture change. So that's where you have seen, for example, in the case of A to D converters, the shift from Nyquist single thread converters, such as a single pipeline A to D or a SAR A to D, to interleaving, which is essentially a parallel architecture. And it has been the only way to cope with this increase in speed, with this demand for speed that outpaces the ability of the process. Now, this has also been possible because when you do interleaving and you deal with mismatches between the different A to Ds composing the array, then you end up with artifacts, basically distortion. And this has been possible because at the same time, thanks to calibration or digital assistance, we've been able to correct for these artifacts and correct for mismatch. So Moore's law comes to the rescue. The ability to have a large amount of digital processing in a power efficient way in a small area is able to support the analog circuitry to correct for the non-idealities, and therefore we can actually build new architectures that deal with this demand. But if you go to finer lithography, one issue that you're gonna immediately find is that it's not just about the devices. The real bottleneck actually is in the interconnects, the strays associated with the interconnects. And one of the issues, as you see from this plot, is not much the capacitance, the stray capacitance. Indeed, the stray capacitance is a problem, but the biggest issue is actually the resistivity of the interconnects, which essentially means that you need to have they need to do interconnects that are short in distance, and where appropriate, they need to be also wide in order to keep that under control. And there are other problems with fine lithography. Electromigration becomes problematic. And so electromigration obviously is particularly problematic at high temperature, when your die is going at a higher and higher temperature, and when the current density in the interconnects is high. So for example, here, if we have an electromigration problem at this interconnect, the way to deal with it is to increase the width of the connectors in order to relieve the density and allow a lower density. Again, the problem is that this is the last thing you want to do when you want to have a high frequency circuit, because now you are introducing large strays, especially large capacitive strays. So that's a problem. Another problem with fine lithography is device aging. So as you go from one node to the next, there are a number of undesired effects, including hot carrier injection effects and NBTI and PBTI, which essentially result into the fact that as devices operate, their parametric, they experience parametric shifts. Primarily, you get a threshold voltage shift, and in the wrong way, sure enough. So the ability to drive currents drop over time. And this shift in the behavior of the device, this device aging, accelerates when the temperature is high, and again, when for high current operation. So you need to also ensure that the circuits will properly operate over time and for the intended life of the device, or otherwise, over time, your devices won't work as intended anymore. The other issue with scaling has to do with the cost of building chips of this sort, which is going up exponentially, not just in terms of the manufacturing cost, but in terms of the development cost, which obviously include physical design. A big component of the cost is verification and so on. So let's look at some ADC architectures over time, just to set some ideas here. If we, each year at ISSCC or other conferences, there are a number of papers that are published, and it's possible to track the performance of these converters with plots such as the ADC aperture plot, where you show here the input frequency, or rather the Nyquist frequency of the converters, against the signal to noise and distortion ratio here. High-speed converters tend to be those that are up high, and higher performance means being higher in a plot like this. So if we zoom in into this area where we find typically converters used in systems like the one I've been describing, there are actually multiple architectures that are used. And for generally speaking, for higher dynamic range, you will find delta sigmas. Continuous time delta sigmas are becoming commonplace. You will find discrete time converters, Nyquist converters, such as pipeline converters. And you will find other newer emerging architectures, such as VCO ADCs. And as I mentioned before, for very high frequency and perhaps a little less linearity, you will find time interleaved data converters. Oftentimes, either pipeline ADCs, interleaved pipeline ADCs, or successive approximation ADCs that are also interleaved. So here are some recent examples, some published examples that obviously I'm more familiar with, and it's an example of this is an example of a 28 nanometer 10-bit 10 gigasample per second ADC. This is a 8 times interleaved ADC. It's in fact a 7 times interleaved with an extra channel that is used to rotate the order and scramble additional mismatches. There is a main buffer that drives the entire array of ADCs, and everything, of course, is being calibrated. Not just the individual converters are calibrated for things like finite gain in amplifiers or mismatch in some of the passives, but also the different channels are calibrated to correct for gain error, timing skew errors, and offset mismatch. And this is a snapshot of a spectrum after calibration. So much of the spurs are very low. You can see the second harmonic, the third harmonic here. You can also see some of the interleaving spurs that after calibration are reduced to a negligible level. And this is a bit of a diagram showing the entire chip. As you can see, the actual converter is only a small part of it, but there are also a number of other blocks that need to be used to make it work. This is a second generation. This is a 16 nanometer, 12-bit, 18 gigasample per second ADC, which was recently published by one of the analog devices team at SSCC only a few months ago. You can see here die photo. Again, you can see the array here with eight sub-ADCs, which are pipeline ADCs, and the digital block, which does much of the calibration. There are a number of innovations being made here to achieve this performance, and the one very remarkable thing is that the power consumption to accomplish this performance, it's of the order of only 1 watt. And this reduction is partly due to the shift from 28 to 16 nanometer, but it's also by and large the result of some architectural innovation, and including the fact that many of the stages are really open loop. They use very minimal amplifiers with very simple but very fast architecture. But then all the non-idealities that come with these simplifications are calibrated. So, for example, finite gain, but also the distortion introduced by these simpler, faster amplifiers. That distortion, if it can be modeled, then it can be calibrated. And another architecture that is emerging is the continuous time pipeline ADC. And this comes from the fact that with, as I said before, processes, the speed or supported by processes is not enough anymore for the bandwidth. And so in order to be able to sustain a wideband delta sigma and sustain the dynamic range, it's becoming prohibitive. So a new architecture has emerged that try to blend the advantages of continuous time converters with the advantages of pipeline converters. And so here, a pipeline ADC, it's really realized with continuous time stages, where you have here the quantization done with a flash, which in turn drive a DAC and creates a quantized replica of the input. And then the input is subtracted by this quantized replica in order to create a residue. The input here is delayed in order to meet the delay between the flash ADC and the DAC, and it's delayed with the delay line, which is LC. And then, so when this one and this one match, we can realize the residue over here and then amplify it with a transconductance, with a continuous time transconductance amplifier, and then each stage does the same. And as you can see, this way we are able to digitize a signal as wide as more than 1 gigahertz with very high linearity and low noise, and able to sustain a high dynamic range, basically all the way to full scale. One other architecture that is emerging is the one of VCO ADCs. And I'm not going to spend a whole lot of time, but essentially you can think of that like if you drive a VCO with an analog input, and so the frequency of the VCO depends on this analog input. And now for a set amount of time, you count the number of zero crossing that the VCO experience, then you can essentially translate the analog input into a frequency, and the frequency through counting to a digitized readout. And so you basically digitized your analog input. Now it's a lot more complex than that, but that's to give you the idea. Now, why doing that? Well, because if for a VCO you use a ring oscillator, a ring oscillator is essentially, by and large, a digital circuit. And therefore, it benefits of Moore's law scaling. And so that really gives us the real advantage of using an ADC, a quantizer of this sort, is that it scales very well with Moore's law. It can be made extremely small. And we have been able to see advantages of the order of 5 to 10 times smaller than similar ADC architectures. And its front end is continuous time, so it's easy to drive. And again, it scales with Moore's law. Now, the problem is that a converter like this tends to be lower resolution and not often is the most power efficient, although there is improvement in this sense. So one thing that we did to marry the advantages of the continuous time pipeline with the VCO ADC has been to build a hybrid ADC, also presented a couple of months ago at IEEE, where the front end is a continuous time pipeline stage, and the back end is made with a VCO ADC, with a quantizer that is done with a VCO ADC. Now you can see here that the front end stage is really larger and the back end stage is much smaller. So we take the advantages of the quantizer made with the VCO ADC, which is size, and the advantages of the front end, which gives the higher dynamic range. And once that, of course, has been resolved, some of the bits, we can use a lower dynamic range quantizer. And by doing so, we are able to digitize 800 megahertz of spectrum with very high linearity and extremely low power. We're really talking about 280 milliwatts versus prior generations, they were well into the watts range. So what do we do with all of that? As I said, that now we have a large wideband system that is composed of different blocks, some high frequency blocks, some millimeter wave blocks in BiCMOS, a transceiver, which includes the converters, the clocking, and some digital function, which typically is in CMOS, and possibly some filters that also needs to be integrated. So let's integrate them into systems on a package. So here comes another technology that we need to keep in mind, which is packaging technology. And common packages for systems like this include BGAs, flip chip BGAs, which allow to have a large pinout and a good amount of performance in terms of frequency response of the interconnects. As I said before, one issue is to dissipate the heat. So it's possible to add heat sinks, copper done with copper plates and heat spreaders, so that the heat can also be extracted from the top part of the die. For millimeter wave, unfortunately, it's common to have smaller packages, and that is because they offer the best frequency response at high frequency. So these are examples of millimeter wave front-end modules and their corresponding packages. And here is a slide showing you trade-offs. The better packages for RF performance tends to be very small, and examples are the wafer level chip scale packages, which is shown over here, where effectively the die sits on a small set substrate with balls and connects directly to the PCB. On the opposite end, we have the BGAs, which allow much larger size, so you can put larger dies. They have a larger number of larger pinout number of IOs, but they don't perform equally well in terms of RF performance due to the higher parasitics. For systems on a package, people are beginning to use 3D packaging, where different dies are stacked on top of each other. So you can imagine, for example, the RF and the analog in separate dies, or some of the analog and some of the digital processing on a finer lithography packaged together. Now, packages like this resolve many issues, such as, for example, the die-to-die interconnects are obviously very short, and there can be plenty, but they also have their own issues, which is prominently the ability to extract the heat when you obviously have hot dies stacked on top of each other. So emerging technologies for systems on a package includes interposer technologies, where multiple chips can actually sit on a common substrate, which can sometimes be a silicon interposer, so that it experiences similar thermal expansion than the chips themselves, which obviously is an important advantage. And the silicon interposer is also used to allow the interconnection between the different dies that sit on the same package, so that you have plenty of IOs that can interconnect the different dies. And then a fewer set of interconnects actually go through a substrate and end up in the actual package and finally on the board. If we look into the future, similar 3D integration is also going to be happening for devices. Devices are going from planar MOS to FinFETs, from FinFETs to gate-all-around and stacking devices. And there is work being done for technologies in the next 10 years, where there will be 3D stacking of devices on the same die. Now, that has some advantages, obviously density, so you can continue packing more and more devices. There is an advantage in terms of local interconnects. Obviously, when you go up to the third dimension, you can actually have a tighter interconnection between the devices that are stacked, which obviously helps, and reducing parasitics, reducing interconnection can also help with power efficiency. Now, the biggest challenge, obviously, is cost. These are very expensive technologies. And heat management. When these devices are going to experience a high temperature, how will we be able to extract temperature, especially where this can be fairly localized? So as I mentioned, in addition to all of this, we can actually leverage algorithms to help out with all the electrical issues. So what I'm going to show you here, just as an example, is an example of a digital pulse distortion, which we developed recently. The issue is the following. let's say that you have a signal chain with a mixer followed, this is a receive chain, a mixer which drives a buffer, and the buffer, after an anti-aliasing filter, drives the ADC. Now, the combination of the driving buffer and the ADC results into a certain amount of distortion, some of which is attributed to the ADC, but in many cases, much of the distortion actually is attributed to the driving buffer, and especially distortion can arise because of the mutual loading between the driving buffer and the ADC. And if you consider that in some cases this may be discrete, meaning there is a separate chip for this one and a separate chip for that one, and then they sit on a board, and then on the board there are a number of non-idealities that come into play, including the fact that the traces may not be balanced and so lead to higher even order harmonic distortion. The issue is we can have a very well-designed ADC and we can do a good job on the driving amplifier, but once they work together, you experience distortion. So can we remove that with algorithms instead of burning more power, for example, in the driver amplifier? So can we solve an analog problem, like the problem of the distortion of this block, with an algorithm? So that's what we did. So the issue comes down here to identify, to set a model for this distortion, identify the coefficients of this model, and if we can identify that, then we can invert digitally the model and post-distort the combination of the buffer with the ADC. So the digital model can sit on the back of the ADC, which is in CMOS, and so there is plenty of digital processing available there, especially because we probably, and in this case, it is the case, we probably have a microcontroller embedded with the ADC to do the calibration of the ADC in the first place. And this microcontroller can also be reused for doing this post-distortion. So what we do is that we use a stimulus stack to inject a known test signal in front of the driving amplifier. When we do that, we do not operate a signal chain. That means there is no input here. This is done at startup. It's a foreground type of linearization. And we use the microcontroller, of course, to drive a proper test signal. When the test signal goes across the driving amplifier, the filter, and the ADC, we receive a certain output, which is distorted. But we know, because we are generating the DAC output, we know what signal is being applied, and we know what signal is being obtained. And so we can use algorithms to identify the nonlinearity that justifies the difference between what we injected and what we received. So we identify the coefficient C for the model, we store it into a RAM, and we can actually then have an inverse model for the distortion. And by doing so, we obtain, again, this is the inverse model of this distortion. And by doing so, now we disconnect the test signal, we operate the entire signal chain with this post-distortion, and because of that, we can invert it and remove the distortion. Here are some results to show how well this is work. The purple curves are several sweeps done before calibration for the second harmonic distortion and the third harmonic distortion. Notice that here the ADC is clocked at 6 gigahertz, and so Nyquist is from 0 to 3 gigahertz. The blue curves show after the post-distortion what is the second and third harmonic. And as you can see, it has improved nearly across every frequency by as much as 10 dBs. And the effect of the linearization ends at nearly 2.5, 2.7 gigahertz, and that's because this post-distortion use digital filters, which obviously have a roll-off as you approach Nyquist. But for most of Nyquist, you really get a very high improvement in linearity. And this plot is showing you that between before and after the calibration, there hasn't been an effect on the noise, so there is no spurious noise introduced, and also the spurious free dynamic range. So this time linearity is also benefiting of the delinearization. If we apply now a Wi-Fi signal, a wideband Wi-Fi signal, 500 megahertz, then you can see visually the improvement. The blue curve is before the calibration. The red curve is after the calibration. So you can see they are overlapped. The intended channel is properly linear, but what we are removing really is the second, the third, and higher order harmonics, which are gone completely. The blue undesired distortion spurs are gone. So, in conclusion, there are multiple technologies. As I said, there is circuit design, there is process technology, architectures, there is algorithms and packaging, etc. And they all help one another, or they all require trade-offs between one another. So, as I said, for systems that require such a wideband and put so much stress on the performance, it's really very important to have a sense of what the trade-offs are and to look at the design really in a holistic way, looking at every aspect and being able to trade off one thing with the other, and obviously keep always in mind the cost of development. And with that, I'm open to questions.
Well, thank you very much for your nice presentation, Dr. Manganaro. From an industrial point of view, this is certainly novelous. And all about that you told to us, the observations of the subject, the innovations in wireless communication electronics are in fact interesting. So thank you very much. Well, we can begin with the questions. First, we have a question from Professor Jan de Waal. He said, "This is a great topic of huge interest. Thanks, and the question is, how difficult it is to manage heat dissipation in high-density 3D package, especially when it includes power devices, for example, power amplifiers and others?"
Yeah, so yeah, of course it's difficult. So the power amplifier typically will sit on a separate package. So what we try to integrate, it's really with SIPs. We try to integrate things like the mixers together with the converters. We have actually done this a few times. And we're really talking about combined power consumption of a couple of watts. The power amplifier really consumes quite a bit of power and dissipates a lot of heat, so it needs to be on a separate package. People for other kinds of systems, that they are actually able to do integration of digital front ends together with the mix signal. We're talking about, in some cases, order of a few tens of watts, so 10 watt or more. The digital front end typically is done with ASICs that are nowadays of the order of 5 nanometers and consume as bad as 10 to 30 watts. While the transceivers generally are of the order of 5 to 7 watts. So that's just to get a sense. Okay, but it's certainly very challenging, and it's as usual, you can do it, but it costs. And so the cost aspect is very important.
Yes, for sure. Okay, we have another question from Adrian Vincent. He said, "Thank you so much, an instructive talk. Why the transistor FT increase cannot keep up the required pace of the other figure of merit? Is it a fundamental challenge or simply a process manufacturing one?"
So the issue with aging that results into a shift of the threshold is due to, as I was saying, hot carrier injection and NBTI and PBTI. So essentially what happens is that as the device operates at high temperature and experiences high current, there are carriers that gets trapped, that gets injected at the surface between the channel and the oxide, and they become trapped. And because of that, you experience a shift. Now, some of these carriers, they eventually can get released, especially if the current changes direction, but not all. And so because of operating a device at high temperature, so there is a high level of injection, and at especially high current density, then this results into more and more carriers getting trapped, and the threshold artificially shifted. And unfortunately, some of that it's permanent. So at the end of the day, what you need to do is that obviously limit the current, limit the temperature, and ensure that the shift is still within range of your, for example, of your calibration for the estimated life of the device, which is typically 10 years. So it's really a reliability issue that needs to be managed. It needs to be simulated, and yeah, so you live with it. And some of the ways to also get around or minimize this is by, for example, if you do chopping, what you should do is that your devices will experience a current in one direction and then the same current in the opposite direction in alternate way. And so that will help that if there is a certain shift in one direction, when you change the direction of the current, some of the shift is actually reversed, and so you recover a little bit. But nevertheless, it's very difficult.
Yeah, for sure. Okay, I think that's the only all the questions that we have. Okay. Well, many thanks again, Dr. Manganaro. We can also hear very interesting presentations about the circuits and some circuits from ISCC, ISCAS, and JCCC. So this certainly contributes a lot to us. Many thanks again.
Thank you.
Yeah. Finally, reminding everyone that we are going to have several presentations during the next weeks. The next week, we are going to have here the presentation of Professor Gerald Yom from Singapore, and it's going to be focused in the body area networks. And finally, I hope you all enjoyed the talk. I will see in the next talk. So bye, everyone, and take care.
Thank you.